Problem number 14. A spool is made of a cylinder with a thin disc attached to either end of the cylinder as shown. The cylinder has radius r equal 0.75 centimeters and the discs each have a radius big R equal 1 centimeter. The string is attached to the cylinder and wound around the cylinder a few times. At what angle above the horizontal can the string be pulled so that the spool will slip without rotating? Solution for problem number 14. For the spool to avoid rolling, there must be zero torque about the spool's contact point with the ground. This occurs when the string lies on a line that intersects the contact point, which we can show on the next picture. Drawing a right red triangle gives us this expression: sine 90 degrees minus theta equal small r over big R. From here we can find that theta equal 41.4 degrees. That's the answer B, and this was a solution for problem number 14. Problem number 15. You are standing on a weight scale that reads 700 newtons while holding a large physics textbook that is originally at rest. At time t equal 1 second, you begin moving the textbook upward so that by time t equal 2 seconds, the textbook is now half a meter high and once again at rest. Which of the following graphs best illustrates how the reading on the scale might vary with that time? Solution for problem number 15. Note that the center of mass of you and the textbook begins and ends with a zero velocity. Therefore, the average reading on the scale must be equal to the combined weight 700 newtons. There is an upward spike on the beginning because you exert a sudden upward force on the book to get it to starting moving, which thus exerts a downward force on you. Similarly, there is a downward spike at the end. The only possibility for this motion could be explained in graph E, where we have positive spike in the beginning and a negative spike at the end. That was a solution for problem number 15. Problem number 16. A plane can fly by tilting the trailing edge of the wings downward by a small angle theta, called the angle of attack. In still air, a plane with a ground speed v will have a lift force proportional to v square theta, and the drag force is proportional to v square. Consider a plane initially in level flight in still air with a constant ground speed v. If the plane enters a region with a tailwind with a speed w less than v, the wind is blowing in the same direction that the plane wants to fly. How must the engine power and the angle of attack change for the plane to maintain level flight at the same ground speed? Solution for problem number 16. Let u be the relative velocity between the plane and the air. To keep the lift force the same, if u decreases, then theta increases. Since the drag force is proportional to u square, the power supplied by the engine is proportional to u cube, which decreases. So it means that the correct answer is C. The engine power decreases and the angle of attack increases. That was a solution for problem number 16. Problem number 17. A pogo stick is modeled as a massless spring of a spring constant K attached to the bottom of a block of mass m. The pogo stick is dropped with the spring pointing downward and hits the ground with the speed v. At the moment of the collision, the free end of the spring sticks permanently to the ground. During the subsequent oscillations, the maximum speed of the block is next one. Solution for problem number 17. When this pogo stick reaches the ground, it's still accelerating down because force of gravity equal mg and the force from compressed spring is small. But when spring is compressing, it reaches the force of compression equal to mg, and in that moment when the net force equals 0, we have a maximum possible speed of this pogo stick. So it means that we can find what is this compression for this pogo stick spring. So we have mg equal kx, and from here we can find that x equal mg over k. Now we can use energy conservation. Suppose that the potential energy for gravity when this pogo stick just reached the ground is 0. It means that total energy of this system is just the kinetic energy for pogo stick, and that's equal 1/2 mv square, and that must be equal to kinetic energy of this pogo stick in the point of x compression, which is 1/2 mu square, plus potential energy for compressed spring, which is 1/2 kx square, and minus potential energy for force of gravity, which is mgx. Now we can insert this expression for x in this equation and find that 1/2 mv square equal 1/2 mu square minus 1/2 m square g square over k. And from here we can find what is this maximum speed. That will be u equal this expression. And that will be answer E for this problem, and this is the solution for problem number 17.